The liver as a glucose factory. One of the unique functions of the liver is its ability to produce glucose during fasting. The glucose released by the liver into the bloodstream restores blood glucose and allows various cells and tissues to access the energy source they need the most. Glucose production in the liver is a coordinated process between glycogenolysis and gluconeogenesis. Glycogenolysis breaks down glycogen, providing glucose from glycogen stores, whereas gluconeogenesis will use smaller molecules as precursors like pyruvate, lactate, glycerol, and other carbon skeletons derived from amino acids to produce glucose. Both of these pathways, glycogenolysis and gluconeogenesis, are more active in the fasting state. In general, these two pathways are activated by a rise in glucagon and or epinephrine in the bloodstream, which will result in the activation of specific enzymes in those two pathways. The key enzyme that breaks down glycogen is glycogen phosphorylase. This enzyme is activated by the actions of glucagon on the glucagon receptor or epinephrine on the beta adrenergic receptor, causing a rise in cyclic AMP, which in turn activates pKa. pKa can phosphorylate glycogen phosphorylate kinase, and glycogen phosphorylate kinase can then phosphorylate glycogen phosphorylase and activate that enzyme. The outcome of activating glycogen phosphorylase by phosphorylation is to break down glycogen and eventually produce glucose that is released from the liver into the bloodstream. Alongside glycogenolysis, gluconeogenesis will also begin during the fasting state, and that process is also activated by glucagon. Gluconeogenesis will use carbon skeletons derived from several amino acids, including the carbon skeletons pyruvate, oxaloacetate, alpha-ketoglutarate, succinyl-CoA, to make glucose from these smaller molecules, with lactate and glycerol providing additional sources for the synthesis of glucose. Glucagon activates gluconeogenesis by its effects on three key enzymes. These key enzymes are PEP carboxykinase, fructose 1,6-bisphosphatase, and glucose 6-phosphate phosphatase. All three enzymes are upregulated, or the expression of all these three enzymes is increased by glucagon. So gluconeogenesis becomes more active when glucagon is elevated in the plasma. Another important allosteric regulator of gluconeogenesis is Acetylcho. Acetylcho in the liver will accumulate due to beta oxidation of fatty acids by the liver using the former molecules as a source of energy. Acetylcho thus produced will activate the first bypass enzyme in gluconeogenesis, pyruvate carboxylase. The common molecule produced from gluconeogenesis and glycogenolysis is glucose 6-phosphate. The liver is unique in that it has glucose 6-phosphatase, which will produce glucose from glucose 6-phosphate. Without this former enzyme, glucose would not be produced from glucose 6-phosphate and could result in severe fasting hypoglycemia.